Hello. Good evening. Welcome to the stream. I'm Agent Ultra, and on this stream we're going to hack on some Haskell as we do. I'm building a Asteroids clone, and this is what it looks like so far. I gotta use my project directory. Asteroids, exec, asteroids, and here we go. There we go. We just added the score counter. That's up in the top left here, kind of hiding my ship. I've got these asteroids. I got the ship can move around. We can fire bullets. We can blow up asteroids. When we blow up big asteroids, they spawn little asteroids. Not exactly the way we want to yet, so we're gonna tweak that. But there's the gist of it. There's a few more things we gotta do to round out this game, but we're making good progress on it. Score counter goes up. All good. So, yeah, let's get into it. It's one way to win, right? Okay, what do we need to do this week? Well, it was brought to my attention by the one and only Swarm Collective, sometimes audience member on the stream, who decided to check out the project. And thank you, Swarm Collective, for bringing this up. We have a little bit of a memory leak in this program here. So we'll go ahead and fix that first. Okay. So when we go to render the text, the game score, as I understand it, this is where it is happening. Although we should probably measure this with some profiling. But what I think is happening with render text right here is that when we create this surface, right, we're creating it we're using SDL, right? SDL is a C library, or SDL2, but SDL, right? Simple Direct Media Layer. It's a C library. And that means that whether Haskell, like GHC, the runtime, or the C library that's allocating memory, i.e. in SDL, who owns that memory is going to be pretty important to our program, right? And if you look at our entry point to our program, the run function, for example, we initialize things like the renderer and the window. We pass them into our state, and which gets handed down to our loop, our main game loop. We also have to call these quit, destroy renderer, and destroy window functions like you would in C, because by doing this, we're effectively asking the C library to allocate this memory. And so we have to take responsibility for cleaning up after ourselves. I guess in this case, Haskell's not going to Haskell's garbage collector isn't going to just clean up this foreign memory for us with its normal garbage collection routine. So in that render text function, I suspect that we have to actually we have to make a call to destroy the surface we create at some point, right after rendering. I have to free up that memory. So let's look up our API. SDL2, beer. And surface. This should be like a free surface function. Yeah, there we go. So free the RGB surface. All right, and that should get rid of, that should free the memory, or tell SDL to free that is free to tell SDL that it is allowed to free this memory now, basically. All right, so SDL goes ahead and allocates that for us and gives us a reference to it, a pointer. We can hold on to it and do as we need with it. But GHC isn't going to take care of that for us, so we have to tell SDL to go free this now. So let's do that. Free surface, text surface. Let's get our build running too. Why not? Bam, bam. Make sure I got you pulled up there, Twitch chat. Okay, cool. I meant SDL.free surface, I did. Good. Okay, and just to be sure, I'm going to double check that if I need to free the texture that we create from the surface. That might be in the renderer module. Free surface. I guess not. Okay, window surface, no, we don't need that. Textures. Update, destroy textures. Okay, that's why it's just named differently. API destroy texture. That makes sense. So let's do that as well. Destroy texture. Text. Tech. Cool. Everything should behave as before. Good. All right. So, when working with foreign memory, the lesson is always remember to ask who owns this. If you get a pointer from a foreign source, you're responsible for it. So you got to make sure that if you need to clean up memory, you need to clean up memory and do that. Okay, small little fix. So we're going to, when applied, this will fix render text, fix resource leak, and render text. We were holding onto the surface and texture pointers without freeing them. Boom. Okay. That's that. Now what do we need to work on? We need to, let's continue on with the big asteroid blow-up handling stuff. All right, so we snuck together a couple of small asteroids. We want to kind of we want 4 asteroids for one, and we want to update their velocity vectors so that they are going to move away from the explosion position. So figuring out the rotation of those is going to be fun. But we'll figure it out. And then, yeah. So I'm going to add another one here. And we'll add one more. Oops. There. Okay, and then we're just figuring out the offsets of these. Okay, that kind of works for those two, but these ones are, those works on the, but the first two work on the diagonals, adding +10, or -10 and +10. Maybe even make those like 20, make it a little bit more apart. All right, so we blow up that big asteroid there. That's maybe a little more. I don't mind a little overlap. Because they're going to be moving, hopefully, apart. Maybe we'll do 30. Boom. Okay, so that one in the middle, I think, is just from these ones we added here. They're just over top of each other. So we got to fix those. Yo, ISO Vector, what's happening? Long time no see, friend. We're building asteroids in probably the I don't know if it's the simplest way possible, but we're building asteroids in Haskell. How's it going with you? How's the search engine? So the other diagonal is going to be the function here we need. And here. Awesome. You gotta show me. Oh, did I bookmark it? I don't know if I bookmarked it. But if you want to, well, Marlowe search, I did. Hopefully it's still up. Oh, it's dead now. Oh no. It lives on in my heart. I'll remember always. And on YouTube too, so there you go. It was a thing once. What happened? All right, so this is going to be v2, x and y, and we're going to, so this is -30 on both points, so it's going to be the upper left diagonal, that's going to be the bottom right diagonal. We'll want this x to be +30, and the y to be x +30. We want the y to be x negative, or y -30. Hopefully that's right. That is a little sillier. Maybe I just need more parentheses. What did I do? Oh. Yeah, oh, fmap, that's what I'm doing wrong here. Fmap is the wrong operation that I want on this v2. Yeah, as I'm pulling out... Sorry, fmap works on these because we're applying the same operation to both elements of the v2. In this function, I'm creating a new v2, so I don't want fmap there. I think I just want regular function composition. Or application, maybe? Yeah. Clean this up in a second. Let's just get it right first. V2. And now on this one, we want x negative 30. I just want them flipped around. So these are the opposite diagonals. Okay. Now I think when I run this, we're going to get the small asteroids in like 4 corners from the offset of the large asteroid's position. There we go. Boop. There we go. All right. I can blow these guys. So then we just have to figure out their vectors so they can make it go outwards on the explosion. And that'll be that. That is going to take a little research because I'm kind of tired and I'm not sure if I'm going to remember all my vector math right off the top of my head. So we have a point and we want to figure out for each of these corners, these asteroids that we're creating here. We want to set their vectors to be also along these V2s actually. Along these vectors. Yeah, that's kind of what we want. So operation-wise, we can multiply. I don't think. Yeah, it's gonna have to come back to me here. Linear.v2. Help me out here. We can sum and multiply vectors, right? Where multiplication is the element-wise multiplication of each of the vectors. You get a new vector. And we can sum them together. But these vector v2s are local positions. They're not directional vectors like along the unit circle from the position that we want for the velocity. Yeah, scalar multiplication seems probably what I want there. Yeah. I think you're right, sir. Right, we just want to change the direction vector of them, though. So, like, multiplying it out will increase the magnitude of the vector, which is good. Yeah. Okay. The goal is for us to blow up this large asteroid over here in the corner. And the four asteroids we spawn, we want to set their direction vectors to be like away from the center of the large asteroid's position in that frame, right? So we'd have the position, and then we need, yeah, a rotation matrix. That's right. Some cosines and sines to rotate those into the appropriate diagonals. And then we can multiply with the scalar on those to kind of push them outwards. think I have some handy dandy rotate around origin type stuff. We can't use this function exactly, but this general part, this part is actually could be generalized a little bit. That, mm, that could possibly work, actually, this equation. Mm-hmm. Yeah, yeah. Um, yeah, something. Okay. I'm just gonna write out the function that we want to pass this to. Rotate vector. No, we're gonna create a new vector. Yeah, we're just gonna create a new vector. That's what we're gonna do. And then we'll just multiply it out. So we just want to set the velocity vector here. Okay. Merp, merp. All right, so we increased the y on this with this one here, so it's going down. Right. We just have to figure out the right vector for 45 degrees this way. And then we can multiply it by a scalar to increase its magnitude so it goes out faster and moves faster in that direction. So I can think about this in degrees to. Sorry, there's got to be a function, yeah. Yeah, it's usually in the convert to radians, rotate it around the rotation like we do with our matrix and transform it. Yeah. Well, that's not exactly it, but. Yeah. Cosine the radians and sine the radians. Okay. I think we have costs in scope. Some radians. Some radians. So they can be the same value. 270 degrees. In radians is about 4.7. Right, and then we want to do one more thing to that and multiply that V2 by a scalar value to increase its magnitude so it flies away from the explosion, or at least it looks like it does. And if I could type tonight, that would be great. There, okay. Hopefully I have it in scope. Let's say 1.2. Yeah, -1. Probably is. I'm so smart. I don't feel smart right now, though. I'm a little, honestly, I'm a little bushwhacked, but there it goes. Yeehaw. So we can adjust that a little bit, but that feels pretty good so far. What I like about sometimes programming with Haskell is that you don't have to be on your A game in order to like get things done. As long as like you stick on the happy path, follow the types, you know. Sometimes you still need to be a little bit, but there we go. Doing some excess calculations there. We can hard code it. Yeah. Yeah. Because we're cool. Okay. The other one we need 45. We'll multiply them all by the same factor so that they're all consistently moving away at the same rate. I hit execution a little too hard there. And then, oh, I blew up that one a little too fast, but that's because I'm just too good at the game. I hold the world's high score for this game, by the way. Although maybe Swarm Collective has beat me, I'm not sure. All right, okay, let's do a couple more. What? Is that 45 degrees? No, 45 degrees seems like too much. Yeah, 45 degrees is exactly that way, right? To the right of the screen. If we're going like 0 degrees is the top. Let's try this. Boom, boom. There we go. Okay, cool, cool. And then, say like, ooh, 70... roughly. And 90, 180. Oh, sorry, no, 90 would be the right side of the screen. So 45 should be right, yeah. I don't know what I'm thinking. Who knows? 180, not quite. Like, I don't know. 120. Okay. Tweak the numbers. Make them all juicy and nice. Pow, pow. Yeah, I got them. Some of them are okay. Some of them a little messed up. Yeah, this one's looking good. That one. The ones are just a little bit messed up, but that's the general gist of it anyway. We just got to tweak the numbers there to make them all go in the right direction. Cool. And then maybe we can simplify these expressions, since like maybe we could actually like compute what those values are, and then we don't have to actually compute them on the fly. We can just hard code the v2s in there because they don't change, right? So let's see. 360, 340. That's 337 roughly. Do that. Let's do that for this one. Cool. Yeah, so let's do... just show me the circle. Okay, there we go. We want 135. 315, 225, and 45. Okay. 90's at the top. Oh, God. I swear I know this stuff somewhere in my head. Okay, that's what we want, though. 135. For this one, let's plop that in there. All right, so that's for the top left one. All right, we want 45. What's the next one on my list? That's the bottom right one. So I want 315 degrees for that one. This is the one we wanted to go at 5.4. There we go. Bum-ba-dum-ba-dum. Okay, cool. Then the other diagonal, so we want 45 degrees for that one. 0.78, there we go. That should be this one here. All right, and then what was it, 225? Yeah. Copy that, 3.92 roughly. Oops, almost. I gotta flip them around. But yeah, those are the directions I want anyway. Which ones did I... Let's see. Almost right. Yes. Yes. Let's see. This one needs to trade with your diagonal neighbor. All right, so you're the bottom right. Means you need to trade with the top right. This one here. This one can go back to the other one. Yeah. Okay, I think that should work. Let me just double check that. Ow. There we go. Yes, okay. Now you gotta flip the other ones. Alright, so this one can flip with its southern neighbor. I'll grab this one and pop it back up here. Oh, a little too hot on the draw there. Boom. There. Okay, they're all spreading out the right direction. That's good. All right, let's see if we can simplify this expression since all of these numbers are like hard-coded and static. We might as well just construct the v2 instead of running cost and sin on every one because we don't really need to. And then, yeah, should be good to go. So I'm going to bring up my REPL. CZ, there we go. I'll just grab my expression here. Plot that over. I got to import data.linear and all that stuff before I can get access to that. Oh, what is it? Oh, just linear. Okay, my bad. Import linear. There we go. Okay, so we're going to replace this whole thing with that. Let's do the next one. I'll put some parentheses around things, but looks good there. Do the same-ish for the next one. Cool. Pop that in there. Put some parentheses around it. Can't type tonight. There we go. Boom. Next. Last one. And there we go. Grab that, jump back over, paste her in. And then everything should be exactly the same. Ew. Cool. It's a bit uggo. What can we do here? We could name these these velocity vectors, maybe? That might make it a little bit easier to, otherwise they're just magic numbers kind of floating there in the code. Yeah, why don't we do that? That'll be a nice little change. Actually, I've lost track of which ones are which, though. Oh no. That's fine. So when applied, this change will spawn small asteroids. We'll update big asteroid bullet collision handling. Spawn 4 small asteroids and set their velocity vectors away from the center of the big asteroid. Boom. Okay, that's good enough for now. And what else do we need to do for our game? Sound effects would be nice. Animations would be nice, maybe. Should we maybe do menus? Oh no, spawning. We wanted to do spawning, that's right. Okay, so randomness. How are we going to handle randomness? Do we have to do everything in I/O in order to get random numbers in our game, or spawning random asteroids? well, I kind of alluded to this last week. We don't really have to do that. As much as possible, I like to kind of like push my effects towards the edge of the program and kind of do them in one localized area. So that not our entire game isn't written in IO, only parts of it are. All right, if we look at all the places we have this IO thing in, we have it in run, we have it in loop, render, render text, and like a bunch of the rendering functions, but that's about it. Right? Init game state happens in IO, okay. Some more render functions. That's pretty much it. I like to keep that way. So for our random number generation, kind of wrote this code. We did this a bunch of streams back, and I ripped it out and said we'd revisit this later on. And I'm not super sure that we actually need this little interface we built here. I might keep it, but let's look at the typical random library that you get. That is the most popular, probably, random library in Haskell. Is it system.random? Haskell random. I think it's system.random. Yeah, I think it's this one. You can get a pure pseudorandom number generator out of this right away. All right. And random gen is an interface to the pure pseudorandom number generator. I don't think we need IO on this. We do have to pass back the state of the pseudorandom generator, which we had with our pseudonumber interface as well, right? Pseudorandom A, right? We get a value from it, we get some value, and then the next state of the pseudorandom generator. Right, and this would fit into our state of our game. So every time we get a pseudorandom value out of it, right, we put the next pseudorandom in the game, back into the game state. And the idea here is that we initialize this at the beginning and seed it with a bunch of random numbers that we get from like the system's available pseudo-random system that's external to our program that we have to call through IO. And then we just pop a bunch of those values inside, and then we can just call these functions to get some values out. And it just uses a list to go around, so it'll just keep popping them around. So it's not like super fancy or anything. But then it doesn't force us to carry IO around if we were going to do something a little bit more interacting with the system's external pseudonumber generator, like through the operating system. So this is pretty good for our game. But I think we might just use this library directly. Rather than this stuff. So that's what I'm thinking. That's probably what I'm going to do. Let's get rid of it. Okay. Stage that. Remove random module. And then we'll add random here. Yeah, so then we have to just remove references to random from our package in the game.hs, I think it was. Yeah. And jump down to 86. Bam, bam. Okay, we'll get rid of pseudo-random float for now. Bring them back in a minute. Once we convert this over to the random library. Different file. Okay, that should be good. And it is. Just gonna clean that up a little bit. Okay, and then we'll add a commit for adding the random package. Okay, so the same idea, right, with this library is that when we want to get a value out of our random number generator, right, we instantiate our random gen in our however we're supposed to do that, and then we can pass it in to our game state. So how do we instantiate one of these puppies? That's the interface. Get studded random. All right, that's I think we do it. Yeah, restart the process, please. All right, so we get our random gen, our G. And stud random. Oh, takes a function, updates the global generator with a new generator. I don't know if we want the global generator. I think we could have our own non-global generator, can we? New standard gen, apply split to the current global pseudo-random generator, updates it with one of the results, and returns the other. No. Oh, there we go, muck standard gen. Okay, so these two functions are how we can make them. We can either provide our own seed, or we can use the system's, whatever the system has available to generate a seed. All right. Getting our own seed, there's various ways we can do that. We can get like the system time that we start the game at. Something like this where it's not wholly deterministic. I mean, but we can create it deterministically, which is nice. So if we ever wanted to like create our game loop where we provide it with a particular seed in order to debug things, it's probably nicer that way. So let's look at init game state. This is where we'll keep our standard generator that we make. So we get the current time. And that's from SDL.time. I think that's a cint, or maybe it's a float. So either way, generator. Actually, this is just let bound. Let's generate it down here, say. I don't know why I have another let here, but I don't think we need it. Generator. Rangen. Muck standard gen. Yeah, let's give it current time from SDL time. See if that works. A type error. If not, it's fine. We'll fix it. Go to import system.random. Okay, current time is not a float. That's a float. Okay, so that's easy enough to fix. We could just like floor it. Okay, and then we have a rand gen that we can put in our game state. So we'll change the type of that in a sec. Game state generator. Or just call it game state rand gen. Be consistent. Right. Super. Game states. Let's update the type to give it that field. Rand gen is a type of random gen. Standard gen. Stud gen. All right, stud gen. There we go. Standard gen. Yeah. Okay, so that builds. Now we have the random generator. Okay, now we can get random numbers whenever we want. Let's test this out. Let's say in the loop, we're calculating the next state. Let's see, state prime. We update the state. We call update on. That's our physics update. We could do something here where we could just like say every so number of frames we spawn a random asteroid somewhere in the field. Okay. Let's see. Update. Let's not do it in the physics loop. Let's say game state asteroids equals maybe spawn asteroids or spawn random asteroid and we'll give it the current state that we've just the state from last frame. Yeah. Hey, Swarm Collective, welcome, welcome. I gave you shoutouts for pointing out there at the beginning that we had a resource leak there. So we fixed that. Thanks again for the tip and noticing that. Okay, so we have to write some kind of function called spawn random asteroid. So let's go to our asteroid-ish area of the code, render asteroids, spawn random asteroids. Cool. Glad. Yeah. Did you discover it by profiling it? Like learning the Haskell profiling tools? Or how did you come across it? We're going to put undefined here. I'm just going to ask GHC what the type signature is. Okay, so spawn random asteroid. We take the game state from the last frame, and before we do any of the physics updates, we're just going to figure out if we're going to spawn a new random asteroid or not, and then we'll just add it to the deck. Actually, we should probably do this after the physics updates have been done, now that I think about it. Because if we do it before the physics updates are done, then we could spawn an asteroid on top of an existing... We still have this possibility. We could spawn an asteroid on top of a bullet. I think most classic versions of asteroids get around this by spawning the asteroids like off the field and move them in. So Stormcliff says, actually do not profile it. I tried a couple of things on my own. Thinking back to graphics libraries, I started focusing on SDL. Cool. To speed things along, I ended up asking ChatGPT what functions in SDL created resources that needed to be freed. It gave me a few options and that helped me pinpoint it. Ah, interesting. Yes, cool. Yeah, so like obviously that was an easy mistake to make on my part, and totally did. But yeah, that was kind of the conclusion we came to as well. Is that when you have pointers, you know, you gotta be aware of the resource ownership of them. So we're getting SDL is allocating memory for us and giving us a pointer to it, so we have to take ownership of that pointer and do the appropriate thing with it, which is just to free it when we're done with it, because GHC's garbage collector doesn't know that it needs to tell SDL to free it. So cool. Well, that's an interesting way of catching that. That's awesome. Cool. So, yeah, I think before we do the physics update or after we do the physics update, we still have the same problem where we could potentially spawn an asteroid on top of a bullet and do collision detection. I think if we do it after the updates, then the collision detection at least won't happen until the next frame, which, given the size of the asteroids and how fast things are moving, it might give you a free point anyway by accident. Or we could, if the logic that we've set up for asteroid movement allows it, we could maybe spawn it off, like outside of the field, and kind of point it inwards towards the center. And that way, it will, hopefully by the time it gets into the field, it'll start doing the torus wrapping, but we can still spawn it outside of the bounds of our torus shape of the play field. And that way we won't run the risk of giving the player a free point by spawning an asteroid on top of one of their bullets. Oh yeah, it was probably near the end of the stream too when we got it done, and I was just like, okay, we're finished here, ship it. Of course, once we have the basic game structure set up and all of the gameplay pieces in play, we should do a like performance pass on it as well, because we're not really paying attention to performance here. We're just trying to get the game going and working, and not being too mindful of that. And I think that's going to be something to pay attention to, especially if we want it to do bigger game projects, for example, in Haskell, where performance does matter in games. And yeah. So one of those things will be like just doing a quick strictness check, and maybe just throwing strictness on by default on our game and just kind of just going shotgun blasting at it, which might be fine because I can't imagine we need a whole lot of laziness in a game engine. There might be like small areas where we could benefit from it, but that will help. And then of course, resource management, making sure that we're releasing everything we hold and all that kind of stuff too. I mean, another good pass. That'll probably come a little bit nearer to the end. Okay, so whether before or after we spawn the random asteroid, let's just think about how we can get a random position outside far enough of our field that we can do this. So the dimensions of our field is probably something we need to know, which is set by our window stuff, or window config. Our window config. IDPI, graphics contact, position. I guess we're using the default SDL window configuration. What's the size? Like 800 by 600 or something like that? Yeah, it's probably like 800 by 600. SDL window config. Initial size, there we go. Defaults to 800 by 600. Swarm Collective. So you'd be interested in hearing my thoughts on the game engine's ability to measure actual time and updating the game state accordingly. Yeah, that is kind of somewhat non-trivial, but it can be done. Performance counters are a thing. I think SDL has that, at least in a relative sense, from like when the game engine was started. Is that kind of what you mean? Hey, Countorin, welcome to the stream. Long time no see, or it hasn't been that long, but it's good to see you. So yeah, we default to 800 by 600 on the screen size. Coordinates may differ if we're using high DPI, which I think we are, but the size should still be the same. So yeah, let me know what you mean about timing. Like, do you mean like actual time as in like wall clock time? That might be a little bit trickier. But not impossible. Just it's possible. Like a lot of games simulate time. It's like simulation games especially too, right? So it all comes out. Man, that's awesome. Learning functors is the first step. Well, maybe monoids, but functors is good. Functors is great. I remember when I was first starting a Haskell, and just the word functor was like a wall, a conceptual wall. I had no idea what it was, or why you would want to use one, or how you would even use it. I just knew it was a word that Haskellers said a lot. And yeah, good times. But now that I know, I almost don't think about it all that much anymore. Ah, yes. You're referring to how the game runs the same on as many machines as possible. So that's kind of that is what our game loop's doing. It's doing a variable step time loop so that it will run the same on different platforms. I mean, the same as in like the physics integration step will be scaled to how fast the game can possibly run on the hardware. It's really hard to predict if you're targeting a lot of different hardware platforms and you don't know which one our game's going to run on, how fast it'll actually run. This was easier to do on like a console like the NES back in the day, because it was like the hardware was fixed. A little bit harder to do on PC. So you have like what's called the variable time step game loop. So that's why we have the outer loop function in our game engine. This is like if you go way back to the beginning of this series of streams on my YouTube channel, you can find them there. And this outer loop is like the main game loop, and the update is an inner loop that does all the physics integration. And it runs as many times. We figured how many slices it can possibly run in this frame time, and we run it when we integrate as many times as we can at that sort of smaller time scale, so that if the game is running on a slower machine, the way the physics works will still integrate it the same as if it was running at full speed on a high speed machine, and it'll be consistent. If that makes sense. A good blog post for this stuff that I also mentioned that in those earlier streams is Fix Your Time Step by Gafferon Games, which goes through the simplest kind of game loops you can usually do these days all the way up to semi-fixed time step, and then so on and so forth to kind of the most, like, we went as far as this here, this loop here, which is like the variable, the free the physics, the variable time step. And there's one where it goes even further, just a smidge, that you can accrue certain errors, and this will fix that. So it goes even further, one step further. You can do that too. For a simple game like our Asteroids game, it's not going to be a huge issue, but for something a little bit more advanced, where you have a lot of physical interacting entities and high rates of speed and things like that, you know, this will be probably what you want to go with. Oh. Blah, blah, blah. Okay, so spawn. Sorry, I'm getting a little distracted with spawn asteroid stuff. That's okay. Always okay to interrupt me, by the way, if you're just tuning into the stream for the first time and want to ask questions like what the heck is going on with this Haskell stuff. Totally cool. You're welcome. Enjoy. Okay, so let's look at our game state. Maybe not using record updates, record wildcards, maybe. Yeah. Okay, so in our game state here, we need to come up with a new deck of asteroids. We're going to pull out our random generator. All right, out of the game state. And what else do we need? We need the asteroids. Now, actually, we need to put the random gen back into game state. So spawn random asteroid should be game state to game state in order for us to use the random gen. Yeah, that's the only thing that can make sense. So we can't do it like this. We can do it here. Spawn random asteroid. Plain old function composition. Okay, and that leaves us just our hole, which is good. Okay, so in our hole now we can get random positions. We could make this a little bit generic to our window config so that we can resize our window and still spawn outside of the bounds of the playing field, assuming that the window is the size of the playfield. Which may break later on down the road if we decide to kind of change the size of our playfield and render it differently inside the scene. Inside of like a scene, if we want to like make the UI kind of outside the borders of the playfield where the player's playing. So we might want to offer ourselves some kind of affordance for doing that later on by having a definition for that thing. That isn't just coming from the window config. Right? So, we can either declare these like as constants, maybe. Playfield width. Playfield height. Right, and maybe we'll extract that into a structure so at some point in time and make these functions for getting these values out from that structure later on, but at least it's the idea is there. So that's what I mean by an affordance. It's like something you can leave in a space that can encourage certain usage. I don't know if that makes sense. Let's look up the word affordance. So it offers an animal. In this case, the animal is us, right? We're animals too. It's a resource or support that the environment offers an animal. Use or purpose that a thing can have that people notice as part of the way they see or experience it. So, like, leaving this idea of the playfield size and things like that leaves us an affordance so that when we want to refactor later on, we have this concept kind of already in there. We can gravitate towards that. We don't have to fully flesh it out right now, but we can gravitate towards it later, if that makes sense. Hopefully it does. Because a lot of things I think probably don't make a whole lot of sense sometimes. I try to make a lot of sense though. Spawn random asteroid. Where were we? Okay. So now that we have that, now we can figure out where we can randomly generate a position outside of this box. Right, so we have to generate a position less than the asteroids. We can make it like a significantly wide margin outside of 0, 0. All right, and if I can find my pen. I'll draw it for you. Yes, kind of like leaving yourself a to-do comment. All right, so if we have our play area like this, it's 800 by 600, then we need a random number that is like negative, say 30, negative 30. All right, is greater than this, but less than, or maybe we can make it a little closer. Say like negative 10. Negative 10. And negative 30 would be the lower bound. Right? So we want to spawn it in kind of like this outer area, this band here near outside this box, like somewhere in here. Right? Could be here, could be here, could be over here, somewhere inside this little band, and then we want to point its directional vector towards the center of this play field. It's a velocity vector in that direction. So then the idea is that this is well outside the bounds that any bullets will exist in the scene, because the bullet logic will transport the bullet when it reaches this point over to this side, but not inside this band here. So there's the possibility that a flying bullet out could despawn this asteroid before it has a chance to hit the playfield. That's definitely a possibility still. with this design. The other thing we could do to prevent that is we could put like an invulnerability flag on the asteroid. So that invulnerability flag will... we could put an invulnerability flag on that, or we could... we could special case the collision detection with bullets so that when they're off screen, off the playfield area, they don't count for collision detection anymore. And then we could safely move that asteroid into the playfield area without it despawning off screen and counting as kind of a free point to the player. So we'll have to keep that in mind. Let's put that in our to-do list. We'll do one thing at a time because that's a fair bit of work to do. And we'll do the spawning in part first. Okay, so random asteroid spawning. It's going to be a multi-step process here. So spawning off screen. Special casing, collision detection, collisions with bullets. And that should be it. So 2 things to do. We'll just add a little note to this one. When a bullet is outside of the play area, it shouldn't count towards scoring or collisions. Yeah, that looks good. Okay. Okay, so we have to choose a number that covers this area. All this yellow stuff. Okay. So our random number generator function under system.random. I'm going to clear up my drawings here. We can get 32-bit values, 64-bit values. We can get a range, no longer used. Oh, okay. No longer used, deprecated. So we can't use gen range. Okay. Are there helper functions that can do like a range? Oh, uniform. Uniform, maybe. Examples. Oh, no, okay. I see. Uniform R. Okay, there we go. Uniform R. I think that's probably what we want. Okay, so we can generate X first. I could use the random number mod 359 as a degree around the yellow band. Mm-hmm. Yeah. Yeah, so we'd have to get uniform R on X, and then we can do that for Y as well. And then we'll get a point somewhere in that band. And we can use that as the position of our asteroid. That's part one. And then part two will be the vector, the velocity vector towards the middle. All right, so let's say a pos X, uniform R. Takes our our range and our G, rand gen. That's going to return 2 parts. So then we get that. So we get like negative from negative. I guess it'll infer our A's. So we get negative 30. To play area width. Plus 30. Play field width. Sorry, I'm silly. Blah, blah, blah. All right, let's try for A pos Y. Okay, and then we're also going to only spawn an asteroid in a certain condition too. We don't want to do this every frame, obviously. But I think we can do that with a guard. So anyways, I'm not going to get distracted from this. So we got the A position X and position Y. And we need to generate a new asteroid. And asteroid position. Asteroid velocity. Well, we have a spawn. We have a make asteroid. We have a constructor for this. That's right. What did I? Was it spawn? Was it spawn asteroid? Yeah. That's right. Let's just focus on smalls for now, and then we'll randomize small versus big. Try and take a small baby step here. Okay, so instead of position here, hard-coding that, we'll use our calculated position. And this will be a pos x modulo the playfield width. $359? Yeah. Try that. And a pos y. This wants to be floats, so we're going to convert those to float from integral. Okay, and then we just add it to the deck in the game state. So we can just do game state, game state asteroids equals game state asteroids of game state with snock. Yeah, I could do it like that. There. And then, of course, we have to pass in the rand gen prime prime. The last state of the random generator. Oh, and we already pulled out asteroids, so we just do here. Okie doke. That's part one. Part two is the vector, the direction vector. We want it to be wherever we've picked the position, we want it to point to the center of the playfield. That's going to be trickier. Given two points on the plane, here, say, and here, what I want is a unit, some kind of unit vector that points to the other point, and then I want to multiply that unit vector by like some amount of speed that I want to give to that velocity. What's the thing I want to Google it for? Yeah, 0 to 359. So the uniform R will keep the value within the range that we give it. So the X value will be Negative 30, anything from negative 30 to playfield width, say, plus 30. So that's 800 plus 30, that'd be 830. We can even hard code that in. All right. If we don't hard code it in, that just lets us change playfield width later on. Right, so we just want to exclude a big gap in between of values on X. All right, we don't want 0, we don't want 10, right? So yeah, modulo the playfield width isn't going to work because that'll be anything inside the playfield width. But no, if we do mod the playfield width and then add the playfield width, that would be well, that would be everything on the other side. It wouldn't do left-hand side. We'll have to fiddle with this, of course, to get the formula correct. Yeah, to visualize the problem for you. Right, we want some range of values for X within here and here, but we want to exclude the middle of this interval. Right, so what happens if the random number generator gives us, because we can only specify the bounds of the uniform distribution, and it gives us a value here. Right. Well, that's no good for us, right? So we could say, you know, let's generate just everything inside, like randomly inside this gap, generate like a value inside that gap, and like maybe have some kind of choice function that can choose between the two. We could do a mod around the minimum and maximum, which wouldn't change this a whole lot, right? So we still run into that problem. We want something in this range here, in this range here. And then conversely, the same thing for the Y, and that'll cover all of our band around the edges. All right, so let's just leave that vector part. Let's get the guard in, and then we'll just at least test that the random spawning happens. And then we can start tweaking the parts of it that matter, that we have to finish. So put our guard condition here. That's true. Yeah. That'll cover us too. Thanks, Swan Collective. Yeah, so Swarm Collective is suggesting that we increase our max bound on, say, like, by convention on the left-hand side of our range. And then if we find a value in here, then we just add the play field width so that it ends up on the other side. Yeah, that's a good one. Nice and simple. I like it. Okay. Okay, so I gotta finish this up. We will definitely keep a note of that. And then I gotta get going because the stream's gotta end in a few minutes. Okay, so la, 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 la. We could say if the game state accumulator current time of the game state and um, let's say it's a multiple of every thousandth tick, something like that. I can't use integral float. Okay, I have to convert this to a float first. I don't need the. I was just being a little paranoid. The parentheses, don't need it. Super. Okay. What's the problem here? Real frack-a-bool. Yeah, I thought I needed to get that all lined up. So line all that up in there. And then our otherwise case, we do nothing. We just return the game state. Okay, fix this, and then we should be good to go. Okay, we should be spawning asteroids kind of like crazy. Okay. It's probably my condition for not hitting it quite right, but unfortunately, that's all the time we have today, but this is how we're going to go about it. That's a little bit of the taste of randomness in pure code. All right, so we do, just a review, in a game state is an IO function. IO game state. We create a random generator using the Mux standard gen, using the current time. We could this could allow us to pass in like a seed as an argument to our game startup code. So later on, if that's kind of what we want for like debugging purposes, that'd be great. But for now, we're just passing in current time just to make things kind of work. Get started. And there you go. So then from there, we can just pull out our standard generator, call random functions and stuff. We just have to remember to put it back in to our game state when each time we use it. Now that can get kind of annoying. There are ways we could clean up the code if that becomes a problem. And, you know, we'll figure that out in the next stream when we finish this code. So I'm going to put this as work in progress and push it anyway. As well as the to-do. Okay, so I'm going to mark that as a work in progress. Add spawn random asteroid. Okay. Now, all the code you've seen here today is available on GitHub. If you're just tuning in for the first time, welcome. Thanks for watching. The public repository here, I'm Agent Ultra. It's on my GitHub, Agent Ultra, under Asteroids. You can also find me on the Fediverse as Agent Ultra there on types.pl. And of course here on Twitch. If you're just tuning in, of course, give us a follow. And you'll get those notifications if you have them turned on for this stream. Sometimes I do surprise streams, but most of the time my regular schedule is on Tuesday evenings at about 10 after 8 in the Eastern Standard and Eastern Daylight time zones. That's all I got for tonight. Thanks for tuning in. We'll see you next week. May all your monads be free and your types always check. And of course, check out declarative.tv as well. There are lots of cool folks who also stream in functional programming languages and declarative programming languages. We have a cool Discord server where you can join in and talk about the project, about your own projects, and what you would like to see on the stream sometime. So peace out. Take care.